Good evening, all of you. My name is Anil Yadav, and this is tutorial 8 on fundamentals of micro and nano fabrication. So, today, most of the slides are taken from Professor Shankar Kumar Selvaraj's course on fundamentals of micro and nano fabrication. So, I will be following his lectures. You can also find his lectures on NPTEL itself, they have given, and also on YouTube as well. So, if you want to get more depth into that. So today in recent previous class we have seen the same basics of the lithography above, and we have covered the types of photoresists and properties of photoresists we have covered in the previous session. So today we will go in a bit more advanced in lithography, initially we will see the contact and proximity lithography, and that we have already covered in the previous session, and then we will move towards the illumination and projection lithography. So which we will see the optics of the this projection lithography. And okay, let's see. So now, optical lithography systems that we have already seen are some kind of one was the contact lithography. In that one, there was a with the mask there was a wafer. Here there was no projection. This projection optics was not there in that one. Instead of the projection optics, that is a contact lithography. In here, the wafer is in close contact or close proximity with the mask itself. Okay, so in that one there are some limitations in that part. So that we will see. Okay, resolution unit. Okay. Okay, let us we will see some more parts. Okay, I wanted to see what kind of okay, let us see get going on this thing. So okay, let me check once if there is someone. Okay, no. In optical lithography systems there are basically that we have seen is three kind of lithography systems that we have seen. One is when the wafer is in close contact with the mask and in close proximity. If there is a small gap in, that is also a contact lithography in the sense, and that this kind of lithography can be realized with the same system. But with this projection lithography, there is a different system is there. So in that one, there is a projection lens setup. Projection optics is there. So optical setup is there to go for a smaller feature size is that than that of this close proximity or this contact lithography can give. Okay, so this is kind of similar to the camera, optical camera, so that we can zoom in and zoom out. There is a projection system of the lenses also in the system, in the camera itself, camera as well. And and the best part of this one is the main advantage of this projection lithography is the size of the feature size. We can go up to 4x kind of the feature size. Like if you have a 400 nanometer of the wavelength of the light, then you can go with the 100 nanometer. You can write 100 nanometer of the feature size with that. Okay, so this is the advantage of this one. And this is the thing which allows the reduction in the feature size that present in the mask. If you have a mask with the 100 nanometer of the feature size, or let us say with our optical systems with the from which that we have already seen, we can write masks that is around 2 micrometer of the feature size we can write. So with this one we can go up to 500 nanometer of the feature size we can go up to, that is reduced by 4. The present tools can reduce by 4. So maybe more advanced tool can give say 800 500 800 nanometers of the feature size in the mask itself, and then we can go by 4 of that. Okay. This is the proximity printing. Proximity printing is, there is a lamp source and there is illumination optics. This illumination optics makes sure of the parallel wavefronts of the lights. Okay, parallel wavefronts is like this, parallel wavefronts of the light, so that the light should be in the unidirectional. There should not be spherical kind of wavefront should not be there. Okay, so and the wafer plate is in distance with the masks, so this is the proximity. So there is a gap in between the mask and the wafer, but there is no projection optics is there in between the mask and the wafer. Okay, the gap is normally filled with air or N2, because to reduce the contamination because of the mask and the wafer, because wafer is coated with kind of photoresists. Okay, if we coat the wafer with the photoresist, then this resist there may get stick with the mask and it can contaminate further. Subsequently, if we write the if we want to print that mask or the same kind of features on the other wafer, then it may contaminate. So that is why there is a gap is kept in between the mask and the wafer, so that it should not contaminate. Okay, and this is a kind of lithography tool. Here in this one there is a nitrogen which is there is kind of exhaust. This is exhaust which is which is required for the for this lamp. Okay, this setup is itself is a lamp setup, which is HG lamp is there, and this is the optic setup which makes sure of the parallel of the let me change the color of the pen. That makes sure the parallel parallel UV light will fall on the on the mask. Here at this position there will be this is the mask, and below that there is a wafer over that, and we can control the parameters from here. So there are some recipes that you can control from here, like what is how much time you want to illuminate your mask, your wafer through the mask, and what and also you can control the dose as well. Let me check, someone is there. Okay, so you can check. You can also give the dose as well. Dose in the sense how much dose you want to power kind of this you want to give to the like 70 millijoule per centimeter square you can give. So you can also control the dose as well. You can, if you want to with the constant power, or if you just want to give for 10 second, 5 second, 10 second, also you can control the time as well. Okay, so this is kind of a near field Fresnel diffraction is there in that one. So we will see what how this looks like. Okay, in proximity printing, so let us say this is the gap in between the this is the opening of the mask. Okay, and this is the gap in between the wafer and the mask. This is the mask, this is the wafer which is coated with the photoresist. This is the photoresist. Okay, this photoresist. So this wave, this light, UV light that we have shown, which is parallel, this will fall on the mask, on the wafer coated with the photoresist. So it will there will be some chemical changes in the photoresist that we have already seen. So it may get dissolved, or it may inhibit the dissolution. So, and also so now we need to see the optics of that to get the better feature size here. Okay, so in this opening, all these points will act as a source. Okay, all these points will act as a source, and these source will be, there will be a spherical kind of wavefronts will be there, and these spherical wavefronts will be kind of interfere constructively on the mask here. Okay, so at this position these are constructively interference, and there will be a higher kind of we can say intensity than the other parts. In this region there will be intensity is higher than the other parts of on the photoresist. So so there was a contrast curve, right? There was a contrast curve like this, there was a contrast curve. So in this one there is the energy is there. So before this energy there is no this energy, this is the kind of the critical energy, we can say the critical energy. And the if the energy of the waveform of this light is less than this one, okay, is less than this E naught, then there won't be any effect on the photoresist. Okay, so in this region, above this region and below this region, the energy of this of the light is lesser than the E naught, so there won't be any effect on the photoresist. Okay, but in this region, this particular region, there the energy is greater than E naught, and there will be a chemical changes, there will be chemical changes in the photoresist. So that is why it will affect the dissolution of the photoresist in a developer solution. Okay, so now comes the resolution limit in this kind of lithography, the proximity or the contact lithography. Mainly we are talking about the proximity lithography, where G is the gap and lambda is the wavelength of the source that we are using. Okay, G is the gap, and then W, the minimum feature size that you can get that depends on the lambda and the wavelength of the light that you are using, and G is the gap in between the mask and the and your substrate or wafer. Okay, this is the resolution limit. Okay, so if there is a more spacing in between the mask and the this and your wafer, so this we can say if the spacing is increasing, then the resolution is decreasing. Okay, line width that you can see is decreasing. Okay, this line width is decreasing. Okay, this is the thing. And okay, this is what we wanted to talk. And now why there is a penumbra effect. Penumbra effect in the sense, so as there is a wavefront, because of then at the edges this waveform, this light is coming parallel, there are parallel wave fronts in this one. So at this position there is a bending of light. Okay, this kind of effect is coming. So because of that we wanted to expose this much area only. Okay, we wanted to expose this much area only, but additionally this area is also getting exposed because of the diffraction. Okay, and light is much if the light source is much larger than the object shadowing. Okay, light source is the effect appears penumbra effect because of that diffraction. Okay, and this diffraction is causing the exposure of the light in this region, which is okay, this was the delta, this was the W, but you are getting delta W as well. Okay, delta W is this much plus this much. This delta W, the feature size you wanted was W, but because of that penumbra effect, 2D tangent of theta is this much of feature size, you are getting W plus delta W feature size. Okay, so this 2 is coming because of the symmetry of this exposure on the both the sides. Okay, this is the thing. And now let's come out to the contact lithography. In contact lithography, this penumbra effect is minimized because of there is in contact there is this 2d 10 theta is not there. Okay, so whatever feature you there is on W, okay, W, that will be directly transferred to on the substrate. Okay, so it will be parallel, and this much of the feature whatever there is opening, that will be exposed to the exposed, and there will be chemical change. Okay, so in this one the main thing is the wafer and the mask are in close contact. Okay, wafer and mask in the close contact. This is the same setup that we can use for both, because there are some settings that we can just do. Here you can select the even how much gap you wanted to keep in between the mask and the wafer. 1 micron minimum, 1 micron you have to keep. Okay, minimum 1 micron you have to keep, otherwise there will be some damage on the mask itself, because if there is some small particle itself that can and the particle is hard enough, so that particle can cause some scratches on the mask, or this photoresist is soft. Okay, that photoresist may get stick on the mask, and that can hamper the features for the subsequent lithography processes. Okay, and also now, okay, let us see other things. In subsequent slides you will get to know more about these kind of lithography techniques. Okay, and okay, let me check. Okay, so and because there is no projection lithography in this one, so only illumination optics, which is not that much critical kind of, in the sense critical in the sense which is not that much we just need to make the line parallel, make the light parallel. So there is a combination of lenses and the mirrors that can make the lines parallel, make the lines in a parallel fashion. And so this kind of lithography technique and this kind of lithography machines are not that expensive, but there is a limitation in the feature size. Okay, you cannot go that much feature size beyond the whatever you have on the mask. Okay, but in other kind of lithography, if there is a projection optics is there, in those lithography techniques, that lithography technique, you can go much below on the feature size. Okay, if you have a 2 micron feature size, you can with on the mask, with that feature size you can write 500 nanometers of feature size. Okay, and the problem with this is contact process is a bit dirty, defective, and kind of these things may happen with the mask. Alignment is done using through the mask positioning that we will see. Okay, that we will see how you can do the, if there are some multiple layers of you want to transfer the pattern, then how can you do that we will see. Okay, in contact lithography, okay, this is the there is contact and proximity lithography is seen in shown in this figure. So this is the mask, this is the resist, or these are some positions that are given with the gap G. If you keep the G gap G with which is at A, if you keep the mask at A and resist which is in the close proximity, okay, which is in the close proximity, so the pattern transferred from the mask, so this is the mask to the wafer or to the resist, will be kind of a this block. Okay, so this will be kind of a from a like a block, and if as you increase the gap in between them, so there will be a tapering will happen because of the diffraction, and so this will start increasing and increasing. So this delta w which is equal to 2d tangent of theta will increase. Okay, 2d tangent of theta will increase, so these kind of will increase. Okay, so and also there will be a distortion in the feature. The features may come, a kind of taper may come on the features because of the contrast curve, as if you will compare it with the contrast curve, that will happen. That we will come back on the contrast curve with this with these kind of things later on. So at that point you will understand clearly. And now the exposure doses. So this is the desired pattern you want to transfer on the from the mask to the wafer. Okay, this is the desired pattern. So if the pattern is overexposed, okay, overexposed in the sense ki if you wanted to expose that this photoresist through the mask for 5 seconds, let us say you have done it for 8 seconds or 10 seconds, what will happen? There will be a rounding of the corners. Okay, the corners will get rounded, and there will be a reduction in the feature size because of that. Okay, because you have exposed it more for longer time, that is why. If that pattern is, if you wanted to, let us say wanted to expose it for 10 seconds and you have done it for 5 seconds, okay, in that case there will be a rounding, the feature size that you want is desired was let us say 2 micrometer, then you will get a more than 2 micrometer, let us say 4 micrometer, 5 micrometer you can get. So this is not desired, actually this is not desired, because if there are lines that are okay, that let us say there is a feature size for the FET mask or a diode or whatever you want to make. Okay, so if you are making a field effect transistor, so this is the source, this is the drain, so and there is a feature size of 2 micrometer, and you have done the patterning like this 2 micrometer, but you are not getting 2 micrometer, you are getting let us say you have done this kind of underexposed, so there will be a feature size is more, and then that, so maybe this area that also depends on the what kind of features you are using, what kind of mask you are using. It may be bright field or dark field kind of masks that we will look into. If you are exposing this area or you are exposing this area, there is kind of one photoresist is known as image reversal. Okay, so in that one, whatever you are exposing, you can dissolve that. Okay, that is positive tone resist or negative tone resist, that depends which type of resist you want to choose. Okay, so there are some things exactly exactly you won't get these things, but this is for the positive tone photoresist. You are getting for overexposed and underexposed. If you are getting for the negative tone, this will get reversed. Okay, this will be vice versa. For the negative tone resist, this will be an underexposed pattern, and for this will be an overexposed pattern for the negative tone photoresist. Okay, this is the thing. Now, one most important thing is the alignments. Okay, so you have some features. Let us see. Okay, just a minute. Okay. You have some features. You want to write the mask. You have some layers. Okay, first layer and second layer. Let us say you are making some maybe with different kind of contacts. Let us say one contact you want to deposit gold, and other contact you want to deposit silver, maybe with the heterojunction kind of thing you want to make. So in that one, different kind of contacts you would like to make in for a FET. Let us say for FET only. So one source is you want to make a gold, and this you want to make silver AZ. Okay, so for this one you need to do lithography twice. Okay, first you will do for the gold deposition, secondly you will do it for the AZ deposition, and that should happen key. This is the feature for the gold, and that should be in close proximity with the for the next layer. This AZ should come here only, so it may come here, somewhere else. Okay, so that won't work for you, right? So the feature that you want to transfer, it should be like this only. Okay, that then only there will be a channel length or channel width will be there, so that should be there. Otherwise there may be misalignment also. So how will you do that is, okay, let us see that how two layer kind of lithography. First you deposit one layer and you have transferred the pattern, and also in that mask you will at the, okay, this is your mask. At this corner and this corner you can do the alignment marks. Okay, this will be there in one mask. Okay, this is kind of a alignment will be there, and in the next layer what you will do is you will align this plus mark with this one. Okay, here you will align this plus mark with here in here. So then, and this at this position there will be kind of this bottom, any one of these can be there in the bottom first, and then you can also at these two alignment marks you will align it for x, y and theta angle. Okay, there can be if you want to make this one, this is the rectangle, that can come like this as well. Okay, this is a kind of, because of rotation also that can happen, so you need to make it correct. You need to rotate it in this direction so that it can come. Okay, also another thing is, if this is there and this is there, so in this one you need to make it like this and like this. So in this one you want to move the mask or the base, that should not be this mask, and at this point this mask and this wafer should not be in very close contact. Okay, there will be some gaps, then only you can move the mask. Okay, so then only you can move the mask from the wafer. So at that point what will happen is you will align these marks and then expose again. Okay, then you do the development and do the this kind of evaporation of the contacts and do the lift off, and you will get the desired features on the mask, on the wafer. Okay. Now let us see the next thing. Okay, these will align like this. Okay, this will align like this. So in this one you can just do this kind of lithography. Okay, one point is this, one part is this. Okay, this is your feature size, this is your feature size, and when you combine both, first layer is done with this one, second layer with this one, then when you combine this will come, and after the final result will be this one. Okay, after lift off. Okay. Now in summary, with contact and proximity printing or proximity lithography, the advantage is this is very low cost and very fast process. Okay, this is very low cost and fast process. You can just in minutes you can do the lithography of this for this one. This is very ideal for the research purpose because of the limitation in the resolution, limitation in the feature size. You can you can do up to 2 micron 1.5 micron of kind of feature size. You can get it easily. Okay, but if you want to study for the materials, electrical and electrical properties of the material, you can do this, use such kind of lithography techniques, but not for the commercial purposes, like for mobile phones, for display applications. For that you can. Okay, resolution is limited reproducibility. In this one, this is reproducibility means the mask. Okay, sometimes what happens is when in a close proximity, your mask is damaged. Okay, so because of the damage in the mask, these are kind of not reproducible sometimes. And sometimes while developing itself, sometimes it is overdeveloped, sometimes it is underdeveloped, sometimes it is overexposed, underexposed. Because of these kind of conditions, their reproducibility and mask lifetime, because of the close proximity, there are some scratches can come and all these things can happen. Okay, wafer and sample defects, they can be there because of the close proximity itself. When you do the close proximity, when you stick the mask with the wafer, so there is kind of some aberration is there, and because of that, this can damage the wafer itself. Okay, and after every lithography, after every time, you have to clean the mask with the acetone, because on in acetone only these photoresists get dissolved, and your mask is ready to use again. But because of some scratches that can come because of the close proximity or in the close contact, so these masks tend to get damaged. Okay, so you need to take care of that thing as well. Now let's move on the next thing, optical lithography systems. Okay, that we have till now we have studied we have studied this near field diffraction, Fresnel diffraction, which is a contact litho, proximity litho. That if there is a gap and no, but there is gap and there is no gap in between the mask or reticle and the wafer. Okay, so this will be same for everyone here as well, for the far field diffraction as well. Fraunhofer diffraction is there. So this is the projection lithography. In projection lithography, there is a projection optics also, so which is in between the mask and the wafer. Okay, in this one, the feature size are projected over the wafer. Okay, the intensity profile through the features is projected over the wafer, which we can magnify, and so because of that we can get a lesser feature size. The most advantageous advantage is because of the you can get a lower features in this one. This is expensive because this projection optics is a very typical kind of thing. Okay, so in this one now, okay, let me check once. So there are some tools for the projection litho. These are the projection lenses, and this is the mask. Okay, so this is the mask. So how this there is a illumination is there. One is stepper, one is scanner. In a stepper, what happens is there is a hole in between, and this through this hole there is a this light, UV light is passed, and that is projection. And over here, this hole is a bit larger, which can be 3 mm 4 mm kind of hole, and this is projected through the lens on the through this projection optics on this wafer. And after that, this what happens is this is a bit faster, because everything the illumination, complete illumination is there through the mask. Okay, but in scanner lithography, or a large area you can do this is bit faster, but there are other problems that come in the stepper as well. But in the scanner you just allow this UV light to pass through the slit. Okay, this slit is of very thin kind of very thin, so that the the intensity of light is constant through the slit. Okay, but in this one the intensity of light is like this now. So if the intensity of light is like this, so the middle the intensity will be higher, at the corners the intensity will be lower. So because of that contrast curve that you can see, there is a the intensity or the energy of the light will be non-uniform across the wafer, and because of that the features are you will get are not perfect. If they make it they may be perfect at some point, and they may not be perfect at the other points. So that is why this scanner projection system is much better than that of the stepper lithography. Stepper lithography is faster, but a scanner is a bit more reliable kind of thing, because you and more reproducible, because in this one both are reproducible as well as, but in this one there is no kind of such what to say intensity variation is not there in this one, but the intensity variation is there. Because of that there will be a different feature sizes. There may be different feature sizes can come, or there may be wedge kind of. Is there any meeting here?
No, nothing.
Okay, tutorial is going on. Tutorial is going on.
Oh.
Yes. Okay.
So,
You can sit here. Okay. Yeah. Okay.
You are practicing something?
No, tutorial is going on. I think there is third floor meeting room is empty.
Empty?
Yeah. So this is an ASML kind of tool, which is a projection lithography tool. So in this one there is a laser at which is controlled by this machine, this computer, and this is this laser is made to fall through the optics to pass through this one, and this is the illumination optics here. Okay, this is the illumination optics in this one, and here is the projection lithography. Here you keep your substrate, or you can say a wafer here, and here you can keep your mask. Okay, here you can keep your mask, and through the mask there is a this pattern on the mask will be transferred through the projection lithography on the wafer. Okay, so now we will see what kind of problems that you may encounter through the with the lithography. So if there is you want to transfer the pattern, and you have kind of a different two-layer lithography you want to do. In two-layer lithography, what can happen is your feature size if maybe what to say if in two-layer lithography what can happen is this may or may not overlap with this one. This feature size may or may not overlap, or there is a, if you want to write a feature here, but it is not getting written by at this point, instead of here it is getting written over here. So because of the translational problem, so there may be a delta x, this mask may be moved delta x in this direction and delta y in this direction. So that is why there is a the illumination of the of light you would like to do at the on the wafer is not at the desired position. Okay, so this may be because of the movement of the mask or the wafer, the relative movement of the mask and the wafer. Okay, if this is the this black one, black curve is for the black rectangle is for the desired one, but this blue one is there is a rotation in the feature. That is because of the some rotation you want to that your mask may have rotated or your wafer might have rotated. So you can correct that by just by the rotation. Okay, there is a magnification. Magnification comes in the projection lithography only, so that they because your feature size is let us say 400 let us say 2 micron of the feature size is there in the mask, and there is a magnification you would like to get is kind of let us say 500 nanometers through that mask. That the magnification which is 4 times there, and you have to set it with the g axis, the relative position of the in between the projection litho and projection litho projection optics and your substrate. You need to move in the g direction so that you can correct this magnification. And another thing is the trapezoidal. So this one comes with the translational plus the magnification, and there may be some lens distortions as well. Because of that you will get some random kind of features. So on the wafers, in this one, this blue is the desired feature size that you wanted to overlay over these features. You are writing through the mask, so that you can see there the rectangles are a bit tilted in this one. So there is a rotational, you just need to rotate in the clockwise direction the mask in the coated or in the clockwise direction, so that you can get a rectangular perfect rectangle that is overlapping with the below one. Okay, and in this one there are two problems that are happening. So one is the rotational, one is the translational. This may be because of the translational only. Some of the features are overlapping perfectly, but some are not. So this may be because of the translational and the rotational. So you have to so there are alignment marks on the wafers and the mask. So so you need to align with that translational in the XY direction as well, and in the rotational as well. So both you have to do simultaneously. One you just do for XY for one corner, and for the another corner you can do for the rotational. Just stick on these two, you will get you can align it very easily. Okay, now so there are some alignment marks that for the lower feature sizes, let us say for 2 micron of the features, you cannot put the alignment marks of higher features, like let us say for 50-60 micrometers of the features you cannot keep as the alignment marks, because you cannot align the 2 micron features with the 50-60 micron of the alignment marks. So there are some rules and regulations that you need to follow. So there is a box in box. This is one box, this is the another box that you that is there in one layer and in the another layer. So you need to align that box. So okay, let us say there is this box. Okay, there is this box that is on the layer 1, and this is on the layer 2, this mask, this one. So that will perfectly fit inside the outer box while aligning. Okay, so in this one, so what there will be X that you know, there is Y that you know. Okay, there is Y that you know, x and y you know, and these will give you the rotational. Okay, if there is a wedge that another one is frame in frame. So this line width can be minimum. There is one line frame is here, then another line frame is here. So on layer 1 what you will write is this one. Okay, on layer 2 this white portion will be in the layer 2. In that one you can align this outer line and the inner line with the mask, with the below layer. Okay, so in that case what will happen is you will be aligning x delta y and also the rotational thing. Okay, so in that you can align both of these things, x, y, and the delta in the sense that the rotation. Okay, delta or theta, whatever you call, you can do that. Bar in bar is another example. So these are the alignment marks that you need to put on your in the mask. Okay, in the two on both the layers that you need to keep on the corners. So at the corners if you will keep, so just two you can put on the each corners on the diagonals. That will be fine for the alignment. Two will be fine for the each mask. Okay, now illumination system, what is kind of this illumination system is there. So this a simple projection lithography system is similar to the optical camera. Desired circuit patterns need to in the mask on that is need to be transferred on the wafer. Okay, that we can do. So there were some so in this one we have increased this projection litho in projection. Because why do we have increased this projection litho? So is this projection litho allows the reduction in the feature size that is present on the mask. So it will give us more lesser feature size which is required for the for to reduce the size of the transistor or any electronic things. Okay, so present day tools can reduce the size by 4. Okay, this 2 micron to 500 nanometer of the feature size you can write. Okay, so this is the projection litho. Projection optics is there, and there is a this kind of lens pupil which is the that we will come what we call it NA. So so that we can control. Okay, that we can control. We will see in the subsequent slides. I just forgot this what to call this one. Okay, this projection litho basically depends on the diffraction. This the basic principle for this projection litho is the diffraction. So and let us say that coherence monochromatic plane wave. Coherent light is the parallel. Okay, which are in phase. The phase difference between the light is 0. There is a wavefront. If there is this wavefront is there, so in this one what happens, all these are at the same phase. Okay, that is why this is a parallel, and we can say there is a no, this is coherent and monochromatic source. So as it passes through a slit, so there is a spherical wavefront is there because of the diffraction, and each point will act as a point source at this slit because of the Huygens principle. Okay, this slit point can be regarded as a new source which will act there will be a spherical kind of the wavefront is there. Okay, but if it passes through a multiple these kind of openings, so there will be different kind of wavefronts will be there, and they will they will interfere constructively and destructively. Okay, and these constructive and destructive interferences can be taken to the mask over the mask. No, can be this is the mask, this opening through the mask can be taken over the wafer, and with the this will be the intensity patterns. Okay, this constructive and destructive interferences will be the intensity of the light patterns, okay, on the wafer, and that is the kind of what to say, that is the your like projection of the mask on the wafer. Okay. uh, Slit and screen can, okay, this is the thing. So there will be interference pattern on your wafer. That is how you will write the mask. Okay. Now okay, let us see diffraction of a coherence light source. In this one, okay, there are some openings, so let us define the terminologies. Let us say W is the opening, okay, that W is the feature of the on the mask, and P is the pitch, that defines the from so that defines the center from the opening to the other center of opening, the distance between the center to the center of the openings. This is the pitch. So there is a constructive interference. Let us say the constructive interference is at this point, the angle between at this is alpha, and this will also be the alpha. So what is the phase difference? That phase difference should be n lambda. Okay, then only there will be a constructive interference. Okay, if delta is the n lambda, n is the n, okay, n is the order of the diffraction, and let us say n can be plus minus 1 2 3 4 5, okay, 0 plus minus 1. So sine of alpha is equal to delta by p. Okay, sine and p is the pitch. So with the a simple mathematics we can calculate this. Sine of alpha is equal to delta by p, and sine of alpha is equal to n lambda by p. Okay, so this is the thing. So this is the phase difference. This is the difference between the not the phase difference. This is the what to say, path difference. Okay, the this wave is, or ray of light is taking a lesser distance, and this is the more distance, that the path difference or between this is the delta, which should be equal to n lambda. Then only there will be a constructive interference, and this constructive interference will give the intensity patterns on the wafer. Now this diffraction of the coherent light source. Okay, so let us see the diffraction of the coherent light source. So there is a P is the pitch, and there are alpha 1, alpha 2, alpha 3, alpha 4, which is because of the order of the diffraction. And if n alpha 1, alpha 2, alpha 3, alpha 4, so these are because of the n is equal to 0 1 2 3 4. Okay, alpha 1 is equal to lambda by p if we keep n is equal to 1. Alpha 2 is equal to 2 lambda by p. Alpha 3 is equal to 3 lambda by p. Okay, the spacing between the orders and the pitch. Okay, so these are the orders of the coherent light source, diffraction of the coherence. So you can which depends on this alpha, the angle alpha, this it depends on the order of the diffraction, and length or lambda, which is the wavelength of the light that we are using, and p, the pitch, okay, the distance between the openings. Okay, so we will in the further we will see more. So in like effect of pitch p, okay, the effect of pitch p in on this one, so which is sine of alpha is nothing but n lambda by p. Okay, let us see. Can you see that the alpha 1 is greater than this one, this alpha? Okay, in this one alpha is more than this alpha. So what is the effect of the pitch P? So let us say this is P1, this is P2, this is P1. Okay, the pitch in this one. So P1, let us okay, alpha in this one is more. Alpha is more than P1. P should also should be less. Okay, because n lambda by P, P is less in this one, P2 is lesser than P1. Okay, this is the thing. Yeah. Okay, so in this one P is lesser. This is the effect of pitch on the these orders, these angles should not be far apart, because there will be some physical limitations of the instrument itself because of the lenses, because they are physical. So they should collect these as many as orders, so to get a better to just to recover the image. Okay, to recover the image of this reticle or this mask on the wafer. So we have seen now we need to, so there should after the diffraction, after the projection, this projection projection optics, there should be an image formation. The image formation will be there. Okay, this how does that image form? Okay, so diffracted light has to be projected on the wafer to recreate the mask. Okay, this pattern should be recreated, the image should be formed on the mask. Okay, on the wafer. Okay, the image is formed as intensity variation, as I told you, there because of the diffraction, because of the interference patterns, there are some intensity patterns. Intensity variation is there because of the constructive and destructive interferences, and that variation is transferred over the wafer, and because of that there is a chemical changes at the higher intensity regions, and which changes the photoresist properties at that positions, and the dissolution of that photoresist in the developer. Intensity variation on the wafer depends on the intensity of each diffraction order. Okay, there are some orders A1, A2, A3. These are the orders. Okay, sign of alpha 1, alpha 2, alpha 3. These are the orders. N lambda 1, n lambda by P. Okay, n lambda by P. N is equal to 1 first order, n is equal to 2 second order. These are the orders. We if more the orders that we collect through the projection or that image we want to recreate the image on the mask, more of the orders, better will be the image recreation. Okay, this is nothing but the Fourier transform pattern. Okay, that we will see in the subsequent slides. So more number of orders that you are collecting, more better will be the image formation. Okay, image formation over the Fourier transform. This is sin alpha is equal to n lambda by P. Okay, so sin of alpha by lambda is equal to n by P, and where P is this is the spatial frequency, n or nu that we can say, which is 1 by P. Okay, or so in this one, in the diffraction spectrum, so in the frequency we can say in the frequency regime, or we can say reciprocal regime, maybe we can say. So with that, if you see, there will be these are the orders. Okay, these are the orders: first order, zeroth order, second order, third order. These are the orders. So as many as orders you collect with the optics of the image recreation, then better will be the image. Okay, just a small example of the Fourier transform, how the image recreation is there. Let us say there is a square wave. Okay, if this square wave can be written in the form of the sine, summation of the sine waves with the different frequency. Okay, So this is the omega is equal to 0, omega is equal to 1, omega is equal to 2. So this with the frequency, with the different frequencies, you can recreate with the summation of the different frequencies all these summations. These are the orders: first order, second order, third order. So this is the we can say the coefficient. N is the coefficient, and these are the different frequencies. If you add all these up with the infinite orders, you will get a perfect square kind of wave. Okay, so if we just want to recreate the image on a just first and second orders are enough just to get a feel of that thing. Okay, so there is an image formation. This is the projection length, and there is a image reconstruction on the wafer at this position. So this projection length is kind of spherical. This is the numerical aperture NA that was given in the pupil that I forgot previously. This is the numerical aperture. Okay, this numerical aperture is a physical limit of this projection optics. So how many of these orders this lens collects will give you a better kind of image on this wafer. Okay. Now, more the number of orders that can be captured by the projection lens, because number of orders, how many orders that this physical lens can collect will give us the image that we will see in more detail now. So you will understand. So how many orders does it require? What is the resolution limit? All these things you will see now. So numerical aperture of the objective lens. So this is the numerical aperture NA that you can physically also control this one. So this is the light that is coming at this projection. This is the mask, this is the wafer. So maximum light, the angle 2 theta p. Okay, sine of 2 theta p, n sine of theta p. N sine of theta p is nothing but this is the numerical aperture. Okay, n sine of theta p. So n is nothing but what medium these lenses are in. Mostly these are in the air only. Okay, this is in the air, so that is the n is the refractive index of the space where is this projection lens is there in the in between the projection lens and the wafer. This media can be some if this is not air, that can be some oil, some water, or anything can be there. So that should not contaminate the wafer as well. Okay, that can be there to get the lesser feature size as well. Okay, NA in the projection lithography can be adjustable as a mechanical element, because as I told you that this is a physical thing that you can remove or you can change the numerical aperture as well for the desired feature sizes. The relationship between theta A and theta B, tangent of theta is equal to, this is the magnification. Okay, m is nothing but the magnification, or is the reduction factor. Whatever the feature size in, let us say feature size on the mask is 20 micrometer. Okay, what you can get on this wafer, that is the divided by m. Okay, divided this you can get on the wafer. Okay, so that is the we can say this is the reduction factor. Okay. Now let us see the effect of NA on the image. Okay, NA on the image, how that will affect is, so this is the physical limit. So okay, so this is the NA of the first NA1, and this is the NA for this projection system. Okay, this NA is smaller, NA1 is smaller than NA2. Okay, so how many orders you can collect? Okay, how many orders you can collect? Let us, this is going out, this will collect, this and this. So or maybe these are the 5 orders that you can collect through this NA. So here you can collect a bit more because of the larger NA. Okay, here you can collect more number of orders. Okay, so this will give you, this will replicate the image, or we can say this square wave in a much better way. Okay, in other cases what will happen is there will be a kind of this. Okay, this kind of uh, of this energy profile will be there of the light. Okay, so because of that there will be there will be some problem, or because if you will see collectively with the contrast curve, so that will give you some kind of wedge function on the that will be replicated on the on your substrate, or on your photoresist. Okay, that is not desired, because there will be problem in lift off, because if there is wedge, most of the metal is getting deposit because of there is no undercut. There are some other things that we will see when we will do the etching process. Okay, in that you will understand why we do not need a wedge kind of profile on the this on your photoresist. Okay, so let us see, move forward. So there are because okay, intensity pattern on the wafer, effect of diffraction order. Okay, so what happens is these are the intensity patterns. Okay, over this there is constructive interference. These lines that you can see, these lines are nothing but these are of the same we can say these are the coherent. Okay, these are coherent with the phase difference in between this and this is 0. Okay, wherever they are meeting with the incident light. Okay, because this blue one is the order 1, let us say this this one is a different order 2. Okay, 0th or first, this is 0 order, this is first order, we can say first order interference. So because of constructive interference can take place with the when there is a 0 phase difference. So this is at this point there is 0 phase difference, at this point wherever this light is meeting, and at this point there is 0 phase difference. At these points there is a intensity pattern, because and that also sine of alpha is equal to n lambda by p. These also, these are the orders, this depends on the lambda and this depends on the p is the pitch. Okay, so on these positions, at these position on the wafer, you will get the replication of the mask on the wafer. Okay, there will be higher intensity. Okay, let us see, someone wants to join. Okay, there will be a higher intensity at these points, and this will change the chemistry of the photoresist, that will dissolve or inhibit the dissolution of the photoresist in the developed solution. Okay, let us move forward. Now the intensity pattern on the wafer, delta A, this is the first order, this is the second order, or zeroth and first order. Delta A, this point, and delta A, the feature size, okay, that is the P. Okay, the feature size that is replicated on the mask is nothing but the difference in between these two constructive interferences, because over here there will be some kind of intensity is higher. At this point there is higher intensity, and in between these two there is the intensity is 0, almost 0, because of destructive interferences. Because of that there will be intensity is lower than the desired, so there won't be any change, chemical change in the photoresist. So the minimum feature size is nothing but this delta A, which is A2 minus A1. Okay, that you can calculate, and this is the minimum feature size, or we can say that is the resolution limit of this tool. Okay, this is the resolution limit of this tool, and you can calculate this easily from here. And what this m sine of alpha, this m is nothing but the magnification factor, okay, of that we have already seen in the previous section. And from here you can calculate these are nothing but just the mathematics, you can calculate that easily. Okay, now how can we calculate this resolution limit of the projection system? And also that depends on the multiple parameters. Okay, that is sine of plus minus alpha, the first order will be is equal to sine of alpha is equal to plus minus lambda by p. Okay, so which is less than or equal to plus minus theta I, and this is also some kind of a bit tricky mathematics. And this when you derive this one, you can calculate this one also easily, because my mathematics is not that good, that not that great, but you can calculate it easily. That this is a simple mathematics that you will just see that 2 theta I and theta p, there are some projection, and there is incidence and the projection image formation that you can. So finally, what theoretical resolution limit you will get is lambda by Na, nothing but lambda by Na. Na is the aperture, that is the mechanical thing, or you can also, there is maximum Na that you can see can be there. Okay, so it is inversely proportional to Na, which is because how many that we will see in the next step as well. So at least two orders of the diffraction you need for this to replicate the image. Okay, so if this is the lens, this is the 0th order, and the second order should be here at this position at least. So this is the Na, this is Na, that is why lambda by Na. Okay, at least 2 orders you need. Okay, one is the 0th and one is another one is the first order. That is why we have already only taken the first order only. Okay, that will give you the minimum feature size that you can replicate, that is the p resolution, that is the lambda by Na. Also from here also that you could have calculated lambda by p. Okay, there is no Na is not there. Okay, Na is not there because we haven't assumed here at this position. Here we didn't assume any kind of collection optics. Okay, Na is we haven't assumed here. So from here you can calculate. So capturing only the 0th order alone cannot create the image. So at least one diffraction order is required to create the image. So that is why only one diffraction order we have taken to create the image. So more can be there. Okay, so minimum feature size can be lambda by Na. That is why. So now that is the theoretical limit. What is the practical resolution limit can be there? Okay, so in this p minimum by m is the magnification factor or the reduction factor which is there. So lambda by Na is the p resolution. The formula does not capture the constituents of the lithography like photoresist, baking, development, and there are some other things which can be because of reflections from the base, or from the wafer itself, or from the from the photoresist. Okay, so just simply add the p resolution is 2k into lambda by Na. and this 2k is a constant which is less than or equal to 1. Okay, so if the resist process is good, then the k would be we would approach to 0.5. Okay, that will be equal. Okay, k is equal to 0.5, then this will be a good. Okay, so that is the one. The formula gives limit of for the pitch, not for an isolated line. This is okay, if there are some lines that you would like to replicate, that is fine, but not for the isolated line, because there is no pitch in the isolated line. If there is line, there is no pitch, because this is a single line. Okay, there cannot be a diffraction pattern that can be generated from a single line. Okay. Now, what we have seen is the projection. Let us, after the projection, you need to create the image that we have been seeing. That image should be created on the resist. So let us see the image formation, how the image formation is created there. First, there is image contrast. Okay, so what is the modulation transfer factor? Modulation transfer factor is nothing but I max whatever we are getting on the wafer, that I max to the I minimum. Okay, so this is the ideal image or ideal real image. This is the ideal, which is the square kind of pulse there will be on the wafer. Okay, and this is the kind of real, because there is we are not capturing all the orders. Because of that, there will be a slope on the sides of the feature. Okay, so that is the thing, I max minus I min divided by I max plus I min. Okay, so this is the modulation transfer factor. So in this one also, what we will see is the 50% of the fill factor, 1:1 line. Okay, the 1:1 line means that there are some features. Okay, so this is whatever distance in whatever the opening is there, but and there will be opaque region. So that is the like 50-50, 1:1 ratio. There are some lines. So the opening of the line is kind of 50 nanometer, and this opaque region is also the 50 nanometer. In this case, this is the fill factor is 1:1. So I mean, so if I min is equal to 0, this is a kind of the ideal case. Okay, I min is equal to 0, P is less than or equal to the P resolution. Okay, so and the modulation transfer factor will be equal to 1, which is the ideal case. And if this I min is equal to I max, there is no difference in between the minimum and the maximum. So the contrast, this is the same, image contrast will be same. So there won't be any formation of the image on the wafer. Okay, because there is the intensity is same everywhere. Okay, the intensity, if the intensity is same, there is no diffraction pattern over the on the photoresist. Okay, so there won't be anything, them either that will be completely dissolved or there won't be any dissolution. Okay, now let us come on the depth of focus. Depth of focus is nothing but because as there is a this is your mask or resist. So as we are assuming that your mask is or this photoresist is uniformly deposited. Okay, but what if there is a wedge, or there is no this kind of photoresist is not uniform on that substrate? So what will happen is there is some dissolution is more at some places, and some places it is less. So that is why, so we need a depth of focus. Okay, depth of focus, because it may be out of focus at some place, because we are assuming that stage is also a also at a a uniform height. Okay, but some points there may be some wedge kind of error is there. Okay, so because of that, you may or may not get the features properly throughout the wafer. At some point you can get the features, at some points of the wafer which is out of focus, where you cannot get the diffraction pattern, then you won't get any features. Okay, or your features may be more or less, can be there. So to avoid that effect, there should be some depth of focus. Okay, depth of focus delta can be, so if in this limit there should be uh, can be the wedge can be there. Okay, the image on the wafer is in the focus if zeroth first order are in phase. Okay, so and the phase difference between the zeroth and the first order will create the optical path difference, and there will be defocus. Okay, this is the defocus, this is the optical path difference, and this is the defocus at this point. This is the optimal, and this is the defocus limit, and the optical path difference is, let us say, delta is there, and this is something which is the defocus. Let us see how can we calculate this defocus limit. Okay, uh, from the the optical okay, again there is a mathematics, because this is the defocus limit. Okay, delta, this is the defocus limit, that is from the point of the projection lens to the wafer. Okay, that is the defocus limit, and this is the optical path difference. The optical path difference is equal to, this is the delta, this is the delta, and delta minus delta cos of alpha, which is the optical path difference in between the zeroth and the first order. Okay, so OPD is equal to optical path difference is equal to delta into 1 minus cos of alpha. From here, for the alpha, you can calculate this for the small sine of theta. Okay, for small angles, this alpha is small. For small angles, you will get is delta into alpha square by 2. For small theta, this sine of alpha is equal to NA. NA is nothing but the numerical aperture. Okay, sine of alpha, this is okay, so then this optical path difference is equal to delta into Na square by 2. So the depth of focus, I think this is a bit tricky. Now let us this is the optical path difference, delta into Na square by 2. So let us take different scenarios for the optical path differences. If, and that was the delta is the defocus limit. Okay, delta is nothing but the defocus. Okay, so and now if optical path difference is lambda, then there is no difference, no difference between the phases. So at this point you will get the image. Okay, if optical path difference is lambda by 2, that is the pi, let us say the lambda by 2, the part the phase difference will be pi. So what you will get, a image reversal kind of thing. If wherever there was a opaque region, then at that point you will get a more kind of intensity. Okay, that diffraction pattern, this constructive, you will get a constructive interference at that point. Okay, so if there will be lambda by 4, the frequency doubling, sometimes you need a frequency doubling and sometimes you do not need a frequency doubling, because there are some kind of other aberrations that we will see. Okay, now okay, 1 second. Okay, now effect of the resist. So let us this on the image on image contrast. This is the image contrast. This is the intensity contrast interest contrast curve, and this is the intensity of the image. Okay, so this is the pattern that is transferred on the wafer. Okay, what this green curve that you can see, this is nothing but the intensity pattern on the on the photo on the resist. Okay, what you will see is this kind of or you can say that this is the pattern, resist pattern. Okay, this is the opening, this is the not opening, or there will be, you will see, let us say. Okay, so this image nothing but this is the real kind of the intensity pattern you are getting over the resist. Okay, this is the image, this is the real kind of, because if you are collecting all the orders of the diffraction, then only you can get this kind of image. And also your intensity or your resist contrast curve is kind of a step-like function. So this is the E naught, this below this E naught, below this above this E naught there will be complete dissolution, or before this there won't be any dissolution. So at above this intensity, this is the intensity, this intensity will be replicated on the wafer. Okay, so this portion and this portion will be kind of dissolved, or there will be a pattern that will come on the wafer. Okay, other than this because at this position the intensity of the light is lesser than the E naught. Okay, intensity of the is lesser than the E naught. So at this position it won't be okay, it is kind of a converted curve. Okay, so this is actually E naught, this is E naught, and above this E naught the resist will dissolve, and below this E naught there won't be any dissolution. Okay, this is the E naught, below this E naught this is less than the E naught, this is higher than the E naught, and whatever the pattern, this will transfer over the mask. This is the E naught. Okay, this will be transferred over the mask. Okay, this is what I want to tell you. If both are ideal, this resist contrast curve is ideal and the transfer is ideal, then you will get a ideal kind of features on the wafer. Okay, now this is kind of a partially ideal kind of problem. So where the image you won't get it completely, the image is not perfect. Okay, but there will be a kind of like this, because you are not capturing all the orders of the diffraction. Okay, in this case what will happen is this contrast curve is ideal. So above this E naught, there will be a dissolution. Okay, so above this E naught, this is above E naught, so this will be transferred on the wafer. Okay, so below this E naught there won't be any dissolution, so this will be intact, this portion. So above this E naught there will be a dissolution or whatever, that depends on the type of photoresist that you are using. So what we are saying is this is the exposed area, this is the exposed area, this is the non-exposed area completely. There is no reaction in this portion by the intensity of the light. Okay, now let us go on the completely kind of a real kind of situation where you are not collecting all the orders of the diffraction pattern on the image on your photoresist, and also your resist contrast curve is there is a slope in the resist contrast curve as well. Okay, so this is the dissolution. Okay, so Okay, so whatever this resist contrast, that this same will be reflected in the image, okay, or on the pattern, resist pattern. Okay, so this is the dissolution, this is the resist thickness. So resist thickness left at this position, resist thickness is left is higher and then that at this position, so that is the resist thickness that is left after the what to say, after the this uh, uh, after the illumination. Okay, so in this case also there is intensity pattern is there in this one, and there is a slope in the resist contrast curve, and this resist contrast curve slope is reflected in the photoresist after the development. Okay, so let me see, just a minute. Now, in reality, illumination. Let us see what can be there in the illumination. So what we were assuming there is that coherent light source. Okay, coherent that and also like there in ideal source this is point source and plane waves or of perfect coherence. We were assuming that this light is completely parallel. But what if because this source is not a point source, the source is like this. Okay, so some light is coming from this point as well, from this point as well. Okay, so because of that this is coming. Okay, but also light from this point is also coming. Okay, so this point is also coming, so there won't be a coherence. Okay, all the points reaching to the mask at this position are not coherent. Okay, there is already a phase difference at this position. Because of that, different waveforms will be there, or we can say there is a oblique kind of illumination will always be also be there. So this is the alpha beta angle, so kind of with the beta oblique projection will also be there. Real source is kind of partially because of the finite size, not the point size, because of the finite size there will be a partial coherence is there. Okay, so because of that we will see what is the in the oblique illumination what happens is initially, so this is the one illumination when light is parallel, this is one case, and the other case is when the light is oblique. Okay, so in oblique, so there is already an angle, we can say the mask is is not exactly perpendicular to the light that is coming. Okay, there is angle beta is there. So we will now the path difference at this position will be equal to delta L plus delta H. Okay, that delta H minus delta L, because this is already there, delta H minus delta L will be the path difference, because this is extra and this is also extra already here. So delta H minus delta L will be the path difference, and that should be equal to n lambda for the constructive interference. Okay, sine of so from here we can calculate the delta H and delta L. Okay, so in here we can see that sine of alpha, which is equal to sine of beta plus n of alpha by n of lambda by p. Okay, so in this one there are some orders, and if we see the intensity profile, or we can in the diffraction pattern in the Fourier transform, so what you will get is, so because this is for the parallel intensity if there is a point source, and these purple ones are because of the oblique. Okay, so this is there at 0, this is the first order, these are the first orders, and these are the second orders. Okay, so there will be this will be there. So because of that point source, this this is there is some angle at this position, some angle at this position. So also not only this side, you will get a this side as well for the real kind of source. Okay, so that we will see in the next slide, but this kind of the intensity pattern you will get in the partial coherence. Okay, so in partial coherence light, diffraction pattern with the partial coherence light, so you won't get only a single line, or you won't get only two lines, but because of that, this there will be an intensity at in between these two angles. So we take the beta max. Okay, we take the beta max, the incident angle beta. So so we take the beta max. Okay, this is the maximum beta that is coming from the from this point, this corner point. Okay, this is the beta max. Also another thing, this is also coming there, so this is the another beta max. Okay, the same the beta max in the other direction, we can say the minus beta max. Okay, because of that, on the both the sides there will be a, this is not a single line, but there will be a continuous spectrum. Okay, there will be a continuous spectrum. So so because of that, there will be a instead of the constructive interference at a point, but there will be a constructive interference at of or a circle. Okay, so this is the thing. So now what we can see, so it is always not a bad thing that having a partially coherent light. It is deliberately made to be a partially coherent light, and there are some light source which are deliberately made with the different and these are designed to get a better diffraction pattern. Okay, so so this is the first order, this is second order, this is the zeroth order, first order and second order. So so these much orders are taken. This is the numerical aperture, which is this is the numerical aperture. Okay, and the partial coherence, okay, what is the partial coherence, which is the sigma. Sigma is nothing but this is the ratio of the source to the project pupil. So ratio of the source size of the source is nothing but this is the source size. Okay, this is the source size, which is equal to sine of beta max. Okay, that we can say that will be twice of the sine of beta max, and this is the sine of theta p, which is size of the pupil. That total we will see that would be twice of sine of theta p. Okay, twice of sine, because of that this is a symmetric kind of thing. Okay, so this is the partial coherence, and the image, as we know, the image is formed because if we have only two orders, zeroth order and first order, at least first order should be there, then you can get a image. Okay, so what is this in between these two? These are the this is nothing but we can say the resolution limit. Okay, so resolution limit we will see in the next section. So if the distance between these two is nothing but twice of NA divided by lambda. Okay, this is minus 1 by p, this is plus 1 by p, and theoretical this limit, we have increased the resolution limit now. Okay, we have increased because there is a very partial, very small portion of that can be enough to create the image. Okay, first order is there and a small portion of that can be there, because if the p is reduced, p is nothing but the pitch. If p is reduced, this will move outwards. Okay, if p is reduced, this will move outward. And what is the resolution limit? That maximum p. Okay, no, that minimum p, and that there is a overlap of this with the numerical aperture. and this diffraction pattern. Okay, this first order of the diffraction that should overlap with the NA, a numerical aperture. Okay, that will give us a as the image on the wafer. Okay, this is the thing. And maybe we can stop here. If you have any doubts or any questions, you can ask me in the next section, next session. So that will be on the next Tuesday from 6 to 8 p.m. So see you there. Thank you for attending.